Whenever we are dealing with data structures, memory plays an important part. So in this chapter, we are going to see about memory and its location. At physical level, means at the last level, this computer memory consisted of large number of flip-flops. Flip-flops consist of few transistors and which is capable of storing one bit. Very important to store one bit. Flip-flop is employed, and these flip-flops, individual single flip-flops, they are addressable by unique identifiers. If we can identify them, then only we can read and write or overwrite them. So let us think of our computer memory, a giant array of bits which we can read and write. So it would be a large, I'm not going to close it, right? This is a giant memory. And since we are not able to, or we are not very good at thinking in arithmetic in bits, what we do is we group this larger, group all these things into larger groups, and together we represent them by some numbers. How we can do this? For example, 8 bits, we call them as 1 bytes. Beyond bytes, we call them as words, which are sometimes 16 and 32 bits. So we conceptually regard this computer memory as one life-size array of bytes. For example, say 2 to the power 32. Memory can contain various things. So all variables and other data used by all programs, this will be contained in your memory. Also the program code, including the operating system, the OS. So this compiler of your programming language and operating system, they work together to take care of this memory management. But it's important to learn them to understand what is going beyond, which is not seen. Though these operating system does care of it. So when you compile your code, when you write your code and compile means consolidate. What compiler will do, it will examine the primitive data types like integer, float, bool, character, and see and compute that how much memory they are going to need. And the required amount is then allocated to the program, which is the program is running in the stack space. This is very important. Stack space. There are two spaces: stack space and heap space. Stack, the space with this is called stack because the function which get called, the memory gets added on top of existing memory. So if you consider this to be a memory, this will be in the form of plates which are kept over one another, and the last one will be the first to come out, and as they terminate they are removed in the form of last in first out. This is the order. Let us see an example. Consider that you have declared n and assigned x, means an integer array named x, also a double m. Now compiler, it suddenly sees that the code is required to have some space. What space? 4 for this integer, and because this is integer type and 10 elements can be kept, 4 into 2, and double will be 8. So 4 plus 4 into 10 plus 8, that is around 52 bytes. And this is the current size of integer and double, 4 and 8. And earlier it was 2 bytes and 4 bytes. So now this already has been computed. For this 9, there will be 4 spaces. See, 1, 2, 3, 4. For x, it will be from 0, x0, to certain space, means 0 will be up till this point, 1, 2, 3, and 4. So this will be x0, and likewise up till your x10. And then here comes the double. It will be taking 8 size, means 8 bytes. This is the layout of memory on the stack from we just discussed, and stack grows like this. Okay, and if you insert code that will interact with this OS to request number of bytes on the stack for your variables, this will be stored here. In this example, the compiler knows that the memory, how does it look? It knows the exact memory address of each variable because the size are been kept. This is the memory in the form of a stack. So stack also has some stack pointer and stack variable and starting point. It exactly knows the memory address of each variable. In fact, whenever we write this n, this gets translated into something like memory address, and this is the memory address. You don't have to worry about it, but it is internally like this only. Now, if we attempt or to access x10, say the 10th one, we would access the data associated with m and may end up reading some of its speed like this, because up till x9 it's okay, because this is starting from 0 to 9. X9 array always starts with 0 and it will go up to x9. What about 10? X10 will not be there. So what problem is there? That we are going to read m, and this will have an undesired consequences on our program. And when function call another function, again the other function which has been called get its own chunk of stack at this moment when it is called. So it keeps all its local variable there, all local variable, because these are as we see, these are some sort of local variables only, but also a program counter that remembers where in its execution it was, because it has to have some or the other arrangement so that the present one will be known, and this is done by the program counter. And once the function does its work, the memory block is made available again for some other purpose. And if it is statically located variables, the compiler can take care of all of this. Then the question comes about the scoping of variables. We have just defined, and we have said also the statically. So this is kind of a scope. So what is a scope? Whenever we talk about our local variables and the stack, we talk about scope. First is global variables. These global variables are accessible to any of the function or any block of code in your program, while on the other hand, these local variables in a function or a code, these are the braces, everything inside this is called a code. The local variables have in function or this code block, they only exist while the execution is in the function of the code block. So it will be stored in the stack, and as soon as your function does its work or the block terminates, the variable is as soon as that deallocated. And when the execution of the function is somewhat suspended for some instance, for some task, let us say an example, another function got called inside this one, and a function inside a function, we call it as nested function, and the variables are stored on the stack but not active, so they cannot be accessed. Let us take an example to exemplify it. We have test. This is a function. Inside it we have a variable called y, also we have variable x. This is considered to be inside this code only, and we have another function called bar. N, m, these are the local variables of bar. X and y are local variable of test. So when bar, it calls test, because see, at this particular juncture the test is being called here. The function test cannot access the variables n and m. Why? The function does not access these values, and as soon after this, as soon as it finishes, test finishes, the variable x and y are deallocated, because x and y, they belong to test, and they are permanently lost because test N and M means the variables are only accessible N and M when inside bar, not outside. And X and Y are only accessible inside test. So bar again resumes and has access to N and M, but not X and Y. Okay, hope you understood that when something is running, it will be accessing its own local variable, not this M and N. But once it is being terminated, now bar can access N and M. You can have sometimes multiple variables sharing this similar name. This may again cause some confusion. For instance, you may have both a global variable called N and a local variable of function which is again called N. So here we have this N. You can see this is N, this is N, and you have some sort of this formation because this is a test function. Inside this there is a block called for. In this for, N is used. In this again N is used. Here when you see out this line is executed, this would output the innermost 3 and 5. Okay, this N will be 3, N will be 5. So as a rule, when there are multiple variables with a similar name, any reference is to the one which is in the smallest code block enclosing the statement that contains that variable, not this, not this. It will take care, or it will only execute and work upon the local variables. This is the rule. Now, as we have seen just the allocation at stack and primary, now, or say static, now we have to talk about this dynamic allocation also. So we don't have so easy way to statically allocated arrays when we don't know at compile time how much memory a variable will need. In stack we have seen that whenever we are aware of the size like int m or int x10 array, we knew exactly how much we are going to need. For example, just take this instance, int t and c in n. This creates an array of an integers. Here at compile time, the compiler does not know how much memory the array is going to take if we define an array. Say this is of this array, let me rephrase it, int x, this is like this, n. Now user is taking n from the input. Now we are not aware. So at compile time we are not aware how much size it is going to take. So we cannot allocate the space on this stack. Let us see what it says. Technically this is not quite true, since modern compiler let you define arrays even of dynamic sizes like vector type, etc. But we advise against using this functionality and instead do things we write on these nodes. This is because let us go the trivial way. Our program need to explicitly ask OS for the right amount of space at runtime now, not at compile time, but at runtime. This memory, which I indicated earlier also, is assigned to the heap space. So there are two types of memory, stack and heap. So this is called the heap space, since it can be selected from any portion of the space that has not been allocated already. So memory, wherever the free space is there, the operating system is allocate. Okay, this is your heap, now work upon it. And this stack that remains somewhat consolidated or in a good form, memory in the heap is somewhat messier and all over the place. Hence it is called as heap. Now the difference between this static and dynamic memory allocation, let us summarize them. And for dynamic memory, we really need to know about these pointers. Static allocation, dynamic allocation. Let us see the difference properly. First is the size must be known at compile time for static allocation. And the size may be unknown at compile time for dynamic. Static allocation is performed at compile time. Dynamic allocation is at runtime. Static allocation is assigned to the stack, while the dynamic allocation is assigned to heap. In static allocation, it uses first in last out. Okay, or last out, we call it LIFO, last in first out. But here is no particular order of assignment. So this was about memory allocation. We are going to see more of it. Thank you so much. Take care.